All right, we're going to get started again. If you can find your seats, thank you. I hope you all got beer and Cycle Dogs. Shout out to Cycle Dogs. Thank you guys for being here. Okay. Awesome. So at this time, it is my pleasure to introduce our second speaker for the evening, the immortal pirate graybeard, also known as Professor Thomas Quinn, will be telling us about simulating the universe. Tom Quinn is the former chair of the astronomy department at the University of Washington. He has been a, what do I want to say here? Guiding light is probably the words I'm looking for, in the astronomy community for many decades. And we all appreciate him very much, especially coming out and giving the Astronomy on Tap talk. So, without further ado, Tom Quinn.
Thanks very much, and good evening. So Charlie gave you a picture of what the universe looks like as a whole. I'm going to talk about how we simulate that universe using computers, and talk about a little bit about the discoveries we have made as we perform those simulations. Oops, I need the little clicker. Excuse me.
Does it work? We fixed it.
We'll see if it works.
I fixed it.
There we are. Very good. Before I get started, I want to make sure I might use the pronoun I or my. I want to be clear that the work I'm going to present is from a group of people, so I should be using the pronouns we and our when I'm talking about results. And the group is the N-Body Shop. We simulate everything from exoplanets.
Yeah! Exoplanets!
to what I'll be talking about tonight, the universe. And this is a group that started at the University of Washington a few years ago, not quite 1872, but somewhat back then. And it's grown to be a worldwide organization. We program big parallel computers. That's kind of difficult, so we reach out to our friends in the computer science department, both at the University of Washington and at the Parallel Programming Lab at the University of Illinois in Urbana-Champaign. So let me start with what I will not talk about tonight. You're going to have a hard time reading it, but I'll read it for you. So this is a paper that came out about a decade ago, Constraints on the Universe as a Numerical Simulation. And the point of the paper is we assume that our universe is an early numerical simulation. So that we're living inside a simulation, we're kind of weird thing, and investigate potentially observable consequences. So this is kind of an odd paper, but that last part, investigate potentially observable consequences, that's a good thing. Even if we have this really weird hypothesis, we can make testable predictions, and that is essentially the essence of science, so that's a good thing. The weird thing is that, they've got to make an assumption about who is creating this simulation, the creators of the simulation. So that's coming up with a model for the creator is, let's say, should be thought about very carefully. So, so that's not what I'm going to be talking about. Let's move on to the fact that we do live in a real universe that's amazingly large, it's fascinating, it's mysterious, it's actually awesome with all the structures inside it. And how do we investigate that using computers?
Oh, there's a rat, sorry.
Oh, wonderful. Okay. Computers. Okay, so all of you are familiar with computers. All right, I've got this computer in my pocket. Okay. Turns out that this particular computer is probably about 10 times more powerful than the first computer I used to start simulating the universe. And we don't think of using this as a calculating device, but that's essentially what it is. Normally we think of it, right, what do I do with this thing? I send text messages to my friends, I look at videos, I have a laptop there, I will edit documents, I will present PowerPoint. What does that have to do with calculating things? In particular, how would you use this thing to calculate things in the universe? Well, most of you probably know, a computer, even your cell phone, is essentially a calculator. And so to your cell phone or your laptop, essentially everything is a number. So if you type out the text, meet me at the pub, right? Your cell phone, the first thing it does is it converts it into a number, perhaps this number encoded in a special way. Those of you who can observe it can kind of figure out what the coding is, for example, what the number for the small e is. But the point is the text gets turned into numbers. Those numbers get encoded in a radio wave. The radio wave gets received by another cell phone, which immediately gets turned into numbers. And even as it displays on the screen, or for example, the display on this screen, to that computer over there, this whole screen is just one big number. That is, for every little pixel on the screen is a color. The color is assigned a number. And then the whole screen is the concatenation of all those roughly a million numbers. And that's how the laptop works. So my Word document, that's just a very large number. What's even more fascinating is the program Word itself is also just one big number. And it's rather fascinating that a computer can use one number to manipulate, that is in a computer program, other numbers, that is the Word document. So that's essentially what a computer does. And we'd like to harness its ability to do lots of calculations to do calculations about the universe. Okay, so that's the computer as a calculator. Let's talk about the computation. Apologies, this will be the one equation I'm going to give on in this talk, and I'll walk us through it slowly in case you're not familiar with it. We are calculating the mutual gravity of all the galaxies with respect to each other. And here's the formula that I need to calculate. Let me break it down for you. The first part of the formula might be familiar to you. It's Newton's law. Force is equal to, of an object that I label with I, is equal to the mass of the object times the acceleration. F equal ma. The acceleration is how fast the velocity changes. And that is, if for a large mass, has less velocity change for a given force. So that's the first part. Should be everybody okay so far? Okay. The second part, this is a little bit more complicated. What does that force look like when we're talking about gravity? And so what this is a strange symbol here. This means summation. And the point, and this is a key symbol because the force of gravity on an individual galaxy is the sum of all the other galaxies in the universe. And that's what this summation means here. If there are n galaxies in the universe, we have to look at every single other galaxy if we're going to calculate the force on, say, the Milky Way. And then the rest of the formula is just telling you how that force is calculated. There's a constant. This is called Newton's constant, big G. The force is proportional to your own mass, and it's proportional to the mass of the other galaxy. It's in the direction going between you and that other galaxy, and it falls off as that distance to some high power. So that if a galaxy is further away, it contributes less force. So that's essentially what this equation means. This summation here, again, means that you have to do a lot of calculations to get the total gravitational force on a single galaxy, and then you have to do that for every other galaxy in the universe. So if you have n galaxies, you're going to have n times n interactions to calculate. And that's a lot of interactions because there's a lot of galaxies. So it's very expensive, it can be complicated, and its calculation requires the biggest computers we have available. So the National Science Foundation has a very large computer. The biggest computer they have is down in University of Texas, Austin. I was talking to the director the other day, and he told me the biggest user of that facility is one Professor Cristiana Di Matteo. She's from Carnegie Mellon University. And she spends most of her time on that computer doing this calculation. Okay, so that's the challenge in trying to simulate the universe, simulating the gravity of all these galaxies. Okay, let's talk about. Oh, you can't quite read it here. People might recognize where this snapshot is from, but let me read it here. It says Pleiades, NASA Advanced Supercomputer. Okay, so just to give you a flavor of what a supercomputer is. Supercomputer is composed of racks. You can see rack. So there's what? About 20 racks in this picture. Pleiades is a natural, all right, this is a snapshot from the movie. Probably some of you know what movie I'm talking about. For the rest of you, I'll tell you in a second. So the Pleiades supercomputer, we were quite amused when we saw this movie because Pleiades is actually a computer I use. It is composed of 150 of these racks. So there's quite a few more rows of these racks in the supercomputer. The individual rack is filled with about 68 what are called nodes, compute units, and each node has about 20 or so compute cores on it. So we're talking about 200,000 compute cores that make up a supercomputer, and I would like to use every single one of them. Okay, to do my simulation. So that's the kind of computing that we use to simulate the universe. Okay, so let's go back to, so people who are not familiar with this movie, now you might. So this is a clip from The Martian. And if you remember, the storyline for The Martian is that we're trying to calculate the trajectory that will get the spacecraft from Mars back to Earth with a reasonable amount of fuel. And this is an astrodynamicist who's trying to do that calculation. Okay? And so when you see the movie, you might be asking yourself, what is this guy doing in the middle of the computer room? Well, actually, he's looking kind of pained. And really, he's looking kind of cold, right? Because half the power in these kind of supercomputers is used for the air conditioning, to blow cold air through the room to keep the computers from melting. And the really hilarious thing is, he doesn't need to be in the computer room. I could go to my laptop right now, log into that computer. I do have an account. And I can be sitting here in a nice, enjoying a cold one, rather than being cold. So there's no point of him being there. The other thing that's a little bit funny about this movie is that, yes, this is a very important calculation, but he only has to deal with like 8 planets and the spacecraft. He has to put in a little general relativity, but it's not a particularly complicated calculation. He could use just one of those nodes with 20 cores, and that would be plenty to do the job. So, well, it's a movie. But it brings me to the point, he is doing a calculation. That is, he has a specific target he wants to hit. He needs to do the engineering calculation to get that target made. I'm not doing that, all right? I'm fine, right? He can't have Charlie's factors of 2, right? That won't work here. When we're thinking about the universe, the factors of 2, they're okay. Okay? So here's my sort of outline, the difference between what he was doing in the movie. He was doing a calculation, working out the details of a known phenomenon. He knows the result he needs to get, and he's just working out the details. I would like to do simulations where I'm not sure what I'm going to get out. Right? I'm going to throw down a distribution of galaxies, and I'm going to evolve them, and what comes out, I'm not sure how is related to what goes on. So there'll be emergent phenomenon, and what I'm really doing is a computational experiment. I don't know the result. There's a little bit of mess I got to deal with, and we're just going to see what happens and try to learn something from it. And so that's what I want to talk to you more about right now. So I'm going to keep track of my time here. We're doing okay.
Don't worry about the time.
Okay.
They've got nowhere to be.
Well, eventually they're going to get kicked out of the pub. So, right. So the experiment I want to do, people talked about, asked a question about the cosmic microwave background. Here's a picture of that. The key feature here is that these fluctuations are very tiny, 1 part in 20,000 or so. And so the colors here, the red spots are 1 part in 20,000 more dense than the blue spots. And so this is the edge of the observable universe to directly answer the question that was put to Charlie. And we want to see, okay, here's the beginning, essentially the beginning of the universe. How does that turn into something that looks like this? And this is very, and just to be clear, right? One of the tiniest of one of these little dots is going to turn into one of these. But I'm not sure how, right? I'm going to do an experiment. See, first, does this really happen? Second, how does it happen? One of the first results of simulations in doing this experiment was this weird thing that turned up, is that there needs to be more matter in the universe than what we observe. Sure, people have seen pie charts like this before. The stuff we observe, we call them baryons, protons, atoms, mostly hydrogen atoms. That's the things we can see. In this picture, you're mostly seeing that, well, all you're seeing are the ordinary material, mostly hydrogen. It turns out that that is only about 5% of the total matter density. Sorry, mass, energy, you know that general relativity thing, content of the universe. There is a full 26, 27% is material we call dark matter. What dark means it does not, it neither emits nor absorbs light, but it gravitates, and we see the effect of its gravitation when we observe galaxies, when we observe clusters of galaxies. And then there's this really, but just to be clear, this stuff obeys that same formula that I showed you a few slides ago. Then there's this stuff. This is also dark. It doesn't absorb or emit light. It also gravitates, but in a very different formula. Right? It's a formula that Einstein came up with. But we have to include it in our calculations if we're to get the growth of those of fluctuations we see in the microwave background into the galaxies we see today. So, just to summarize the game here, we start out with that First colored picture I showed you of the cosmic microwave background, very small fluctuations. We somehow develop galaxies which are enormous overhead space. The average density in the middle of the galaxy is around 10 billion times the average density in the universe. And we follow that through this process of gravitational collapse. It's the mutual gravitational attraction that causes both the collapse into the galaxies and the formation of the voids that Charlie was talking to you about before. And so the way we do it is we throw in a distribution of matter that mimics the microwave background, and we just simulate, right? See what happens, see what emergent phenomena come out. Okay, so that's the fun game we play. All right, I'm talking about simulating the universe. Even though I have supercomputers, there's a problem here. How do I fit a huge universe? You know powers of 10 from the last talk, so there's roughly 10 to the 80 particles in the observable universe. How are we going to fit those into a supercomputer? Even if you have 10 to the 15 bytes of memory, that's way too little memory to fit the entire universe. So, and of course, you know, if we could do that, then the computer is actually bigger on the inside than it is on the outside. That would be quite the paradox. So what do? Well, we cheat. All right, so the first cheat we do is what I call the cosmic video game. So back when I was in university, we had this fun video game called Asteroids. And if you flew out one side, and you know Asteroids too? Yeah, it's a wonderful. One side of the screen, you pop back in the screen on the other side of the screen. And so we play that same game with our computer simulation. So we wrap the universe around inside the computer. And this is okay if, again, Charlie showed us, on the largest scale, the universe is statistically the same. And so that's how it works. And just to give you a little detail, so here's one of my simulations, one of our simulations. The scale of simulation is such that, like this object is roughly a Milky Way galaxy. So say this whole region is kind of a large group of galaxies, just so that you have the scale. And you can see the filamentary structure that Charlie talked about. You can see the voids that he talked about. But let's look carefully, particularly say the filament going out here. It kind of comes in over here. And that guy up there, right? There's a little piece of that group over there. And there's a little piece of that group over there. And so you can see that how we're cheating there. We're wrapping things around. And just to sort of blow it out, right here, here's that fundamental cube that I showed you before. And I just pasted the same cube around it. And you can see how things match up at the corners. And so when I do my calculation, hopefully things don't break when I do my calculation. Right, I want to calculate the force, say, on this galaxy. I will do a sum over this one, and that 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 one, all the way out. Okay, in fact, we do a sum over the entire universe that way. And that's, right, does make the calculation even harder, but that's how we fit the universe in on the large scales. Okay, but that's not the only cheat we do. We also cheat on the small scales. So even if we do that wraparound trick, we still have the issue that even a small part of the universe is really big. And so we group the particles together in what I'll call in this talk superparticles, where each particle inside the simulation will represent many, and by many, I mean 70 orders of magnitude particles. All right, so 10 to the 70 or so. That's what I mean by large. And even, in the simulation, we model the dark matter. We also model the stars. And when we have a star, we're not talking about an individual sun. We're talking about a whole cluster of perhaps 1 million stars represented by a single particle in our simulation. And that brings up the fact that we do not have the resolution nor the understanding to understand how a single star forms in our simulation. And so we look at the simulation on larger scales. So instead of parsec scales, we'll look at hundreds of parsec scales and say, okay, if the gas is so dense on that scale, then stars will form. Likewise, stars, not our sun, but some stars go supernova. And we can't model the individual supernova, but we have a star particle and we say, okay, a certain number of supernova will be spawned by this star particle. And so that's what I mean by subgroup physics. And then lastly, all right, we don't have to resolve every galaxy in the universe. We can focus on, say, a galaxy that looks like the Milky Way. And we perform these zoom-in simulations where we focus a lot of the computational power on resolving an individual galaxy that we find of interest. Again, maybe it looks like the Milky Way. And just to give you a picture of how we do that, here's one of our simulations. On the largest scales, here's what it looks like. You can see there's, again, the cosmic web and the voids. But we're going to zoom in on this particular galaxy. It has this rather round halo of dark matter, but the actual visible part of the galaxy is only about the 10th of that size, and that's where we have the stars and the gas. And so we had this zoom-in resolution so we can actually look at the morphology of the individual galaxy. Okay, so we put all that together, and what do we get? Here's a simulation. Notice that first was the expansion of the universe. Okay, so you get the Hubble expansion of the universe from the Big Bang, but after a while, you get some of the material ceases to expand and falls back on itself, forming, in this case, we're looking at the dark matter, so this will be a galaxy halo. A couple things about the formation of the galaxy halo. You notice it's not a perfectly spherical collapse, as you might at first guess. You have stuff flowing. These filaments are actually quite important because material is flowing along the filaments into the galaxy. Another, actually, discovery we made when we first did these high-resolution simulations was the amount of substructure that occurs in the galaxy halo. This came actually as quite a surprise back in the day being about 25 years ago, that there was so much substructure. And that was interesting because, well, I'll tell you, sorry, I'll talk about the substructure in a little bit. Anyway, just pictures from simulations. Here's the cosmic web in a simulation performed. This was performed at the time on the third largest supercomputer in the world, supercomputer called Pitt-Stein in Switzerland by Doug Potter and Joachim Stadl. And this is on the scale similar to that Millennium simulation that Charlie showed. We're talking gigaparsecs across. You can see the voids, the filaments. Now, imagine we took maybe a cube of this about so big, and what would that look like? And here's, this is my opening splash slide. This is a simulation. It's 25 megaparsecs across. Well, we talked about what a parsec was earlier. So So megaparsecs, so that's 25 million times the distance to the closest star. That's a good way to keep track of it. And so you have objects, maybe this object is roughly the size of the Milky Way. You can see it has a lot of substructure. You can see that all this filamentary structure keeps going all the way down. That's another result, that we don't see filamentary structure only on the largest scales. Filaments within filaments within filaments is the structure that we see. And this was run on run on about 500,000 compute cores. So it was a computer that was about twice the size of the Pleiades supercomputer I originally talked about. Yeah, now let's talk about the substructure. All right, so here's a picture of one of our simulations. All this dark matter substructure. If you look at a galaxy like our own Milky Way, well, actually, this is Andromeda. Those of you amateur astronomers will recognize that, even though it's all washed out. We do not see the same substructure here that we see in our simulations. We see a little bit of the substructure, but our simulations predict that it's out there, and perhaps if we look deep enough, we might be able to discover it. And this is one of the hopes of the Vera Rubin Observatory, of which the University of Washington is a part. If we look faint enough, we might be able to see the stars that occupy these substructures that our simulations predict. So I'm really looking forward to that. So let's back up. Let me introduce this. Again, this is what the Milky Way would look like if you had dark matter glasses. We don't have dark matter glasses. We see the light, which is caused by the gas and the stars. And so what if we do a simulation where we include the effects of the gas, the stars? What does that look like? So similar, we start out with the expansion of the universe. We get objects start, whoa, what's that? What happened there? So that's the supernova going off. Okay, and this is another effect that was somewhat surprising to us at first, that the supernova going off from dying stars has a significant effect on the gas distribution in the galaxy. And the colors here are showing to what extent the surrounding gas is being polluted by supernova ejecta. And you see, as galaxies merge, the supernova rate goes up, and furthermore, it stirs the gas around such that the gas is not rotating as quickly as it would have if the gas wasn't there. And in fact, the gas is also disturbing the dark matter, which was a real surprise to us. Again, decreasing the rate at which the gas rotates around the middle of the galaxy. So that was another fascinating discovery we made in simulations not too long ago. Yeah, these are just fun to watch. Okay. So we can, I'll show you all these later. Okay. Let me finally say that, okay, you should be asking me, how do you know your calculations are correct? And I worry about that. And one of the things we do is, right, our group isn't the only one writing code to form these simulations. We have several groups, and we've been getting together to compare results. And so these are the same initial conditions, the same starting point, and we use a slew of different codes, about 8 different codes written by essentially 8 different people, or 8 different simulation groups, to do the same calculation, and we can compare results and see not so much what we got right, but what we can trust, because most of us are getting the same answer, and what we have to work on to get better, better predictions, more reliable results. So reproducibility is one of those science things that we need to be doing. and that is indeed what we're doing with these simulation projects. And if you need to know this, and this is from our group. You want to pick out the right one. Okay. Okay. So I told you about some of the simulation discoveries we've made. I just want to put down a couple more that have been key in the study of cosmology over the years. There was simulations that first predicted that galaxies had those round dark matter halos that I've showed you. Simulations also ruled out any of the known, what are called standard model particles, as a possible candidate for the dark matter. That's a key result. That we have to look beyond what the particle physicists currently know about to explain the dark matter. And I have discoveries I am anticipating on making, hopefully in the not too distant future. I'm working about. All right, you saw gas leave small galaxies in that one video. How does gas leave our Milky Way? That's a different story. And I don't understand how it works. Yeah, I'm hoping simulations will illuminate me there. Our Milky Way has a black hole in the center. How many black holes are there out there? Are there black holes in the galaxy not in the center? That's a very interesting question. I'm hoping simulations will give the answer. And ultimately, what is the dark matter particle? What characteristics, or subatomic characteristics does it have? I have hopes that simulations will provide the answer to that. So there are some of the questions I have. You might have some questions, so I think I'll stop here and let you ask them. Thank you for your attention. Let's see. First question I saw was way in the back. Shout it out.
Yeah. So for these simulations, are you typically plugging in actual observed initial conditions like CMB, or is it more like synthetic kind of interpolation?
All right. So the question is, am I using observed initial conditions like the cosmic microwave background, or am I generating synthetic initial conditions? So yes. So the issue is that what made our local universe was not the CMB that we observed. Okay? So what we do is we analyze the cosmic microwave background, look at its statistics. How big are the fluctuations? How did they vary as a function of scale? And come up with a statistical description of the cosmic microwave background, and then use that statistical description to create a random realization that is identically statistical, identical in the statistical sense. Okay? So that's what we do. Okay, we can.
You mentioned substructure. What is substructure?
Well,
Is it just like
all right, so what I'm referring to is, we have, this is meant to be, right, this is a model of the Milky Way, okay? You are like right in the middle here, or nearly in the middle. There, in the Milky Way halo, there are all these sub-halos of various sizes, and that is what I'm referring to as substructure. Okay? Good. Yes, back there.
Yeah, does your work overlap, or can you speak to the so-called crisis in cosmology, which is like the difference between the simulation versus observed expansion of the universe?
Oh, right. I think you're talking about the H-naught controversy. Is that the H-naught crisis? Is that what you're?
I think so.
Yeah. So there's So just to summarize what I think you're referring to, you can derive an expansion rate of the universe from the cosmic microwave background. You get one value, 67 kilometers per second to megaparsec. You can also directly measure the local expansion rate of the universe, and you get another value, 73 kilometers per second per megaparsec. Those are in tension, as they say. And does my simulations address that? Essentially, no. Right, I'm pretty much dependent on the observers to tell me what the overall expansion rate is. Of course, sometimes we put in a fudge factor. If you notice in Charlie's first slide, there was this little h on the ruler. I don't know if you noticed that. That little h encodes our ignorance about the expansion rate of the universe. So that's how we sort of cheat our way around that. And it's not really cheap. We recognize what we know. Okay.
Is artificial intelligence and machine learning impacting simulation?
So, so he's asking if artificial intelligence is impacting our simulations. So, so I'm not the expert on it, but I've been talking to people about how to do this. And so the answer is yes, in that, particularly from my perspective, the subgrid physics are trying to recognize, okay, what kind of configuration is needed to get stars to form? That's a very good question to ask a machine learning algorithm to do. And so that's the kind of things we're doing with artificial intelligence in the computational technology community. Yeah. Okay, time for one more question. I'll let you ask afterwards, and I'm going to take one right there.
Yeah, do you model different characteristics, different temperatures of dark matter, or do you kind of pick one that you're comfortable with and run with?
Oh, no, right, so, right, nature of dark matter. Right, so one of the things we do is, okay, what if we tweak the temperature of dark matter? So we do, all right, most of, so do we change the properties of the dark matter? Sorry, is the question. Most of the time, don't. But when we're trying to experiment and figure out the nature of the dark matter, yes, that's one of the parameters we change. That is, how fast does the dark matter move as a particle? Affects structure formation. Yeah. Okay, I think that.
Do you want to answer your questions?
Okay, go ahead.
I just wanted to know if magnetic fields even exist on the scale, or sorry.
Okay, all right. Just to let everybody in on a joke, right? So, do magnetic fields affect anything in our simulations? Okay, so the joke is that if you go to a research talk and you don't understand anything about it, but you want to ask a probing question, you say, "Do magnetic fields have an effect?" Yeah. So, sorry. I just have to let everybody in on the joke. Right. It probably does. I have not included it here. We are beginning to include it. In particular, one of the constituents that I haven't talked about this evening is something called cosmic rays. So these very energetic particles, they get emitted by, mostly generated by supernova shocks, and their propagation is strongly determined by the magnetic fields. And so to properly follow the effect of cosmic rays on, say, particularly this particular problem, magnetic fields might be the answer to this question here. We are just starting to investigate it. So it is a very good question. Thank you.
Let's give one more round of applause to both of our speakers. Charlie? And just to finish off the joke, when somebody asks you if magnetic fields matter, your response usually is, it probably does. But I don't know how. Okay. And I have one more thing to say, which is that I have asteroids on the PlayStation 2 and the PlayStation 2. If I bring them into the department, will you play asteroids with me? Okay, thank you. Yes, thank you. So anyways, with that, our next Astronomy on Tap will be on October 23rd. We have 2 speakers. I've already lined up speakers, and they're really fabulous. We had the former chair of the department this month. Next month, we will have the current chair of the astronomy department, along with one other professor in our department. So look out for that on social media. If you won trivia, be sure to come get a trivia prize, and get home safe. Did I miss anything? It's good. It's good.